Okay, what's going on here? What is going on? Okay. All right. So if I remember correctly, and please let me know if I'm wrong, but I think the last time we were here, we were discussing this example. Oh, let me share my screen. Sorry about that. Okay, so if I remember correctly, this was the last thing we discussed, right? If I'm wrong, please let me know. We were discussing the example of a redox reaction where we put magnesium in a solution of copper 2 sulfate. And just to remind you uh, of the equations for the reaction that we're talking about here, as soon as I can find my pen. Okay, so the reaction is, if I can squeeze it in somewhere here, is magnesium solid plus copper 2 sulfate aqueous to give magnesium sulfate aqueous and copper solid, right? So that's the equation for the reaction. And in terms of the net ionic equation, I'm going to put it down here. It is magnesium solid plus Cu2 plus aqueous to give magnesium 2 plus aqueous plus Cu solid, copper solid, all right? So that is the net ionic equation. And if I remember correctly, what I was stressing on in this particular case is what is oxidation and what is reduction. So just to briefly remind you, the magnesium is undergoing oxidation, right? Because it is losing electrons, losing 2 electrons. And the copper is undergoing reduction because it is gaining 2 electrons. So this is reduction. And I'm going to see if I can squeeze it down here, gaining 2 electrons, all right? So this is a simple example. We're going to see more complex examples later on, but this demonstrates basically what happens in every redox reaction. Something is losing electrons, something is gaining electrons, and the substance that is undergoing the loss of electrons, that is said to be oxidized, and the substance that is gaining the electrons, that substance is said to be reduced. And I think I gave you this memory aid to help you to remember what is what. Oil rig, did I give you that? Right. Oil rig, oxidation involves loss of electrons, reduction involves gain of electrons, right? So you might find that helpful in terms of remembering what is oxidation, what happens in oxidation, what happens in reduction. Yes, sir.
So with redox reactions, are they, because it involves the changing of the charge, it generally would involve like transition metals a lot of times? Because
yeah, there are many reactions where transition elements are involved, but not only that, but even non-transition elements, right? But yeah, you have, in fact, some example you're going to see here is where you're going to see some transition metals involved in terms of loss and gain electrons. Another thing too I want to stress is that we can look at oxidation and reduction in terms of changes in the oxidation numbers, right? So if you remember, we said that if the oxidation number increases for a particular atom, then we say it's undergoing oxidation, which is what we see here in the case of magnesium, because magnesium had an oxidation state before of 0. If I can get this thing working. Okay, so magnesium has an oxidation number of 0 here, but over here it's +2, so there's an increase. So therefore, the magnesium is said to undergo oxidation. On the other hand, the oxidation number of copper is +2, and over here is 0, so therefore it's undergoing reduction, all right? And then the last thing I want to stress before I leave from this slide is that in every redox reaction, the number of electrons lost in the oxidation must be equal to the number of electrons gained in the reduction, right? You must have that, right? Whatever the number of electrons lost must be equal to the number of electrons gained, all right? In order for a redox reaction to occur. Okay, so with that said, what we're going to do is look at an example, right? And we're going to do several examples, but we're going to start off with this one right here. So very often, in fact, in your assignment number 4, I think the last couple of questions were questions involving balancing redox equations. Now, let me just say that we all know how to balance equations from earlier, right? However, when it comes to redox equations, right, you have to be a bit more, it's a bit more challenging in some cases, right? If you try to balance them in the normal way that you're accustomed to, then in some cases, especially the more complex ones, you might find it very difficult. So there's another method that is used for strictly for balancing redox equations. In some textbooks, they call it the ion-electron method. So I'm going to demonstrate that by doing this particular example. Now, in this example, they give you some information about an equation. It says the oxidation of Fe2 plus to Fe3 plus by this, which is called the dichromate ion in acid solution. Now, let me just say that to be fair to you guys, there's missing information right here. And the missing information is that a product is not mentioned. So let me mention it now. And that product is chromium 3 plus. So let me just put here, okay, where should I put it? Let me put it right here at the end. Producing Cr3 plus, all right? So let's say you're given that information, right? And the question is, how do you go about balancing this equation? Well, the first step is that you'd have to write down an unbalanced equation, right? Based on the information provided, all right? So based on this question here, based on the statement, what would you say are the reactants of this reaction? Based on the information that is given here.
Two of them are going to be, one of them is going to be Fe3 plus and another is going to be
You sure about the Fe3 plus?
It says oxidized, the ion oxidizes from
It says
Fe2
the
plus to
oxidation of Fe2 plus to Fe3 plus. So one of them is a reactant. Which one of those?
A reactant would be Fe2.
Exactly.
Yeah.
The Fe2 plus would be the reactant, would be one reactant, and there's another one. Based on,
Cr2O7.
right, the dichromate, right? Okay, so what would be the products? Now that we have identified the reactants, what would be the products?
Fe3 plus and Cr3.
Exactly. So basically, you're going to write down this equation right here, right? The unbalanced equation, where the Fe2 plus and the dichromate are reactants, and the Fe3 plus and the Cr3 plus are the products, all right? Okay. So that's the first step. Now, in some questions, they may give you this, right? So in that case, you don't need to figure it out because that is provided, right? But just in case you're given a description like this in words, then you'd have to figure out what the reactants are, what the products are, and you set up your unbalanced equation. Okay, the next step is that we separate this unbalanced equation into two half reactions, right? One of them would be the oxidation half reaction or half equation, and the other one would be the reduction half equation. So for the oxidation, that would be the Fe2 plus going to the Fe3 plus, all right? That's one half equation. And then the other half equation is where the dichromate goes to the Cr3 plus, and that would be the reduction half equation, all right? So that's the next step in this process. You separate the unbalanced equation that you figured out in the first place, you separate that equation into two half equations. One of them would be the reduction half equation, and the other one would be the oxidation half equation, all right? Now, the next step is where we balance all atoms other than oxygen and hydrogen in the traditional way, in the way that you're accustomed to doing it, right? So what does that mean? It means that for the first half equation, for this equation here, we don't do anything because we have one Fe2 plus here and one Fe3 plus, so therefore that is balanced, right? In terms of the number of ions present. However, in the case of the dichromate, you'll notice that you have two chromium atoms here, but you have only one on this side, right? So the way we would balance this in terms of the chromium is that we would put a 2 here, right? And therefore, you're going to end up with that equation, all right? So basically, in the third step, you're going to basically balance all atoms excepting oxygen and hydrogen in the traditional way, like I just did in the case of chromium. Now, the next step is actually two steps in combination. I should have separated this, but I'll just go with it. Basically, what you're going to do is concentrate on balancing the oxygens first. And the way you balance the oxygens is by adding water to the side, which is deficient of oxygen. And you add enough water until the oxygens are balanced on both sides, right? Then after that, you balance the hydrogens by adding H plus ions to the side that needs hydrogen in order to achieve that balance. So I'm just going to show you how to do that in this case. Now, in the case of the Fe2 plus the Fe3 plus, there are no oxygens, there are no hydrogens, so we don't need to do anything as far as that is concerned. However, and I apologize for this being so faint, so let me rewrite this down here. In the case of Cr2O7 2 minus to form 2Cr3 plus. That's what we had before, right? You'll notice that there are 7 oxygens here, and we have no oxygens on this side, right? So what you need to do is add 7 water molecules on this side. Because by adding 7 water molecules on the right side, you now end up with 7 oxygens on the right, which balances with the 7 oxygens on the left. All right? So just to recap, this particular step, you balance the oxygens, and this is true for any future problems like the ones we're going to look at later on. You balance the oxygens by adding water to the side, which is deficient of oxygens, right? And you add enough water on that side until the number of oxygen atoms on both sides are the same, all right? Then we get to the balance of the hydrogen atoms. And in this case here, because of this 7 here, that's 14 hydrogens represented on the right. So to balance the hydrogens on the left, we put 14 hydrogen ions on the left side, all right? So now the hydrogens are balanced, right? So you balance the oxygens by adding water, you balance the hydrogens by adding H plus ions, all right? And that's basically it for this 4th step here. So let me see here. So this is the final answer. It's not clear here, so that's why I'm writing this here, all right? So this is what you end up with when you balance the oxygen atoms by adding water and the hydrogen atoms by adding H plus. All right, so after that, the next step is, and this is where, let me just warn you, based on past experience, this is where students tend to screw up in terms of trying to answer questions like these. Because not only must you balance all the atoms on both sides, you have to make sure that you balance the charges. In other words, the total charges on the left side of the equation must be equal to the sum of the charges on the right side of the equation. So the question is, how do we achieve that balance? And to achieve that balance, we follow step 5 here. We add electrons to one side of each half equation to balance the charges, all right? So in the case of the Fe2 plus the Fe3 plus, we did not have this before. You notice that there are 2 plus charges here, and there are 3 plus charges on this side, right? So the charges are not balanced. So to balance the charges, we add 1 electron here to the right side. Let me erase that. So we add 1 electron to the right side, because by doing that, what you'd have achieved here is plus 2 charge on this side and plus 3 minus 1. The electron will subtract 1 charge from that side. So this gives you plus 2. So now we have plus 2 charges on either side, and therefore that particular half equation is balanced with respect to the charges. For the second half equation, let me clear this here. I don't know if, okay, let me just rewrite this just in case. For the second half equation, I'm just going to rewrite what I had up here, which was 14H plus Cr2O7 2 minus to give 2Cr3 plus 7H2O. Okay, so in this case here, same principle applies. We count up the total charge on both sides. So if you count on the total charge on this side, that would be 14 plus charges minus 2. So 14 minus 2 gives you plus 12. And then on this side, we have 2 times plus 3, which is plus 6. The water has no charge, so the total charge on this side is plus 6. So the question now becomes, to which side do we add electrons, and how many electrons do we add? Now remember, each time you add an electron to any side, you're reducing the total charge on that side by 1. So therefore, what I would do is add 6 electrons to this side, right? Because by adding 6 electrons to this side, I'm adding 6 negative charges to the plus 12 charge. 12 minus 6 gives you plus 6, which balances with the plus 6 on the right side. All right? So basically, that's what you do to balance the charges. You add electrons. In fact, let me just say it this way. This is what I normally tell students. When you get to this stage, you look at which side has the higher net charge, right? The side with the higher net charge is the side to which you're going to add the electrons. And then it's all a matter of figuring out how many electrons you would add in order to achieve the balance of the charges to that side, all right? Okay, so that's step 5. So now that we have the two balanced equations, half equations in terms of the number of atoms and also in terms of the charges, the next step, let me clear this here, is we need to make sure that the total number of electrons lost in the oxidation half reaction is equal to the total number of electrons gained in the reduction half equation, right? As we said before, this is true for all redox reactions, right? Whatever the number of electrons lost in oxidation must be equal to the number of electrons gained in the reduction. Now, as we have it right now, here and here, we have 1 electrons being lost here, but we have 6 here, right? So the question is, how do we equalize the number of electrons? And the answer is that you multiply this equation here, in this case, by 6, all right? Because by doing that, you're going to end up with 6 electrons, but you also have to multiply the iron and the Fe2 plus on this side by 6, right? So that is what is shown here, all right? You're going to end up with, when you multiply that equation by 6, you're going to end up with 6 Fe2 plus to give you 6 Fe3 plus 6 electrons. Okay, so after you do that, then you're going to add the two equations together. What's going on here? And when you add, oh, okay, so now we're going to add this equation to this equation right here, right? And whenever you add the 2 electrons, or I should say 2 equations together, you need to cancel out items that are common on both sides, right? Which in this case would be the 6 electrons here that is produced and the 6 electrons here that is used up, right? So these are the 2 equations here. And then, again, let me just rewrite. It's just a 6 electrons plus 14H plus Cr2 minus to give Cr3 plus 2 Cr3 plus H2O, 7H2O. All right? So you're going to add this equation to this equation, right? The 6 electrons will cancel out. All right? Here and here. All right? And then what you do, there's nothing else you can cancel. And later on, you're going to see in some examples that we're going to look at, there are some cases where other substances will cancel out, but that's for later on. So after the cancellation of electrons, what you should do next is simply write down what is left on both sides. So when you do that, you're going to end up with this equation right here. Let me erase this here. Okay, so you're going to end up with this equation right here, right? And that should be the correct answer. However, I would recommend that when you get to this stage, you do a quick check to make sure that everything is balanced, including the charges, right? So let's do that right now. You'll notice that there are 14 hydrogens here, and then you have 7 times 2, 14 hydrogens. So the hydrogens are balanced. You have 2 chromiums here. You have 2 chromiums here. The chromiums are balanced. You have 7 oxygen atoms here. You have 7 oxygen atoms here. So the oxygens are balanced. And then you have 6 iron on this side. And you have 6 on this side. So all the atoms are balanced. But we also have to check the charges. We have to make sure that the charges on the left is equal to the total charges on the right. So let's look at the charges now. So based on what we have here, this 14 here will multiply this by 14 plus charges, right? And then we have minus 2. And then we have 6 times plus 2, so that's plus 12. So that gives a grand total of what? 14 minus 2 is 12, 12 plus 12, 24, right? So that's the total charge on the left side. So let's look at what happens on the right side. We have 6 times 3, which is 18. And then we have 2 times 3, which is 6. So that's equal to what? 24, right? So we have a total of 24 plus charges on both sides. So therefore, now we are confident that this equation is balanced. All right? Okay, any questions about this? Any questions? Any questions? Any questions? No questions? Any questions out there in Zoom?
What was step 3?
Okay, let me back up here. Step 3 is where we balance, I think, all atoms other than oxygen and hydrogen.
You tried that down, sorry. You can go forward.
Okay, so I think it's best that we do some other examples so that you become more proficient at balancing redox equations. So I'm just going to go to Word. I'm just going to make up a question. Oh, this was one I did for my last class. Maybe I should do this one. Okay, let me do this one. Okay, why is this thing not? Oh, okay, let me do this. Okay, what I'm going to do is get rid of all this here. Okay, so let's say you're given this equation and you're asked to balance it, right? Redox, using the method that we just looked at. So let me hear what you have to say. Following the steps that we just did, what would be the very first step once you get this? Based on what we just did.
Write them into two different equations.
Okay, so what would be the first half equation you'd write down?
The oxidation.
Okay, which would be? Tell me what to write down. Tell me exactly. Anybody?
And the NO3 negative to N2.
Okay, NO3 minus to N2, very good. And what would be the other one?
Or
S2,
203.
O3, 2 minus to S4, O6, 2 minus. Okay, very good. All right. So now that we have separated it into two half equations, what would be the next step? Again, based on what we just did in the previous example. The next step would be
Is it to balance the charges?
nope.
Or
That's
just
Balance
Several
all atoms
steps.
other than
Okay.
oxygen and hydrogen.
balance all atoms excepting oxygen and hydrogen. Okay, so what does that mean for the first half equation? Since we're balancing, oh, I'm sorry.
Balance N to N2. So
So
2NO3.
exactly, 2NO3 here. Okay, very good. What about the second half equation?
So for that, it just needs to be multiplied by a coefficient of 2 as well.
Multiply by 2.
The entire S2O3.
Okay, very good. Okay, very good. Right. So we balance all atoms excepting oxygen and hydrogen in the way that we have just done. In the case of nitrogen and in the case of sulfur for the second half equation. All right. Next step. Again, based on what we just did in the example previously. What would be the next step in this process? What would be the next step in this process? After balancing all atoms excepting oxygen and hydrogen,
It's the N2, the 2NO3 to N2 needs to add H2O
to balance what?
to balance the oxygen.
Okay, very good, right. So in the case of the first half equation, to which side would you add the H2O and how many would you add? For the first half equation.
6 H2O to the side with N2.
Exactly. So we add 6 H2O to the right. All right, everybody understands that? We add 6 H2O here because we had 6 oxygens on the left, right? So to balance the oxygens, we add 6 H2O on the right to get 6 oxygens on the right. Okay, very good. What about the second half equation?
It doesn't either,
Right, it's already balanced in terms of the oxygen because you have 6 oxygens on either side. So therefore, in that case, you don't need to add any water. All right? Okay, very good. What's the next step? Now that we have balanced the oxygen, the next step is,
Add electrons.
nope,
Hydrogen,
balance the hydrogens by,
add H plus ion.
okay, adding H plus. Okay, so what does that mean for the first half equation? To which side would you add H plus and how many?
And 6 H plus ions to the left.
Sure about that?
12.
12.
12, right? Because you had 6 times 2 here, right? So you're going to have 12 hydrogens to the left, right? And let me just say 12 H pluses, 12 hydrogen ions, right? Very important. Okay, what about the second half equation?
Still doesn't need. any.
Right. There are no hydrogen, so therefore you don't need to balance it, all right? Okay, good. Next step, and this is where I said students tend to screw up in terms of balancing the charges, right? Because remember, the next step is to balance the charges by adding electrons, right? And remember I said that what you should do, I hope this helps you to remember, you add electrons to the side with the higher net charge. You add electrons to the side with the higher net charge. Okay, so what does that mean for the first half equation? Let's look at the total charges in the case of the first half equation. How many total charges do we have here on the left?
Um, 12H plus 2NO3 would be
To be what?
10.
10, right, plus 10,
Plus 10.
right? And how many charges do we have on the right side of the same equation?
Neutral on the right
0,
side.
exactly, no charges. So, to which side would you add electrons and how many would you add to that side? 10 to the left, exactly. So 10 electrons on the left side. Very good. Usually when I introduce this to students, they mess up on this one, but you guys, so far, so good. Okay. What about the next half equation? How many charges do we have total on the left side here?
Is it -2 or -4?
-4, because you have 2 times -2, right? So this will be -4. And how many charges do we have here total on the right side?
Just -2.
-2, okay. So to which side would you add electrons and how many? Remember, you add electrons to the side with the higher net charge, right? 2 electrons on the right side. Very good. All right, so far so good. All right. So now that we have balanced all the atoms and the charges, the next step would be what?
Or balance the 2 half reactions.
Well, they're already balanced,
Or
but there's something.
balance the charges.
Nope, we already did that.
Well,
What's the next step?
okay, it's canceling the electrons out.
Right, but we have to do something before we cancel electrons.
Oh, rewrite the whole thing.
Nope.
Okay.
What do we do in order, before we can, you're right about canceling the electrons, right? But there's something we need to do in order to be able to cancel electrons. And that is what?
Multiplying by the coefficients.
Right, and the reason why we do that is to make sure that what?
The electrons are.
Exactly, that's the point I was trying to get at, right? We need to make sure that the number of electrons lost is equal to the number of electrons gained, right? So in this case here, how would you achieve that equalization, for lack of a better word? How would you achieve the number of electrons lost be equal to the number of electrons gained in this particular case?
Multiplying the second half reaction by a coefficient of 5.
By 5, exactly. You multiply the second half equation by 5. So when you multiply the second half equation by 5, you're going to end up with 10 S2O3 2 minus to give 5 S4O6 2 minus, excuse me, plus 10 electrons, right? So you end up with this as a result of multiplying this equation here by 5, all right? And what I'm going to do is draw lines through this just to avoid confusion, because the next step is where we add this equation to this equation, right? And in doing so, we have to cancel out whatever common items are on both sides. So what will cancel out in this case when you add these two? Let me write down here at the end, the sum of that addition. What will cancel out when you add this equation to this equation?
Which one?
The electrons.
The electrons will cancel out. So these 10 electrons will cancel out. And based on what I see here, nothing else will cancel out. So basically, what you need to do now is write down what remains, which would be 12H plus 2NO3 minus plus 10S2O3, 2 minus, and then on the right side, you're going to have N2 plus 6H2O plus 5S4O6, 2 minus. And that should be the final answer, right? But again, as always, I would strongly recommend that you check to make sure that your final answer is totally balanced in terms of the atoms and the charges. So let's do that now. We have 12 hydrogens here. We have 6 times 2, 12 hydrogens. So the hydrogens are okay. We have 2 nitrogens here. We have 2 nitrogens here. So that is okay. We have 2 times 3, 6. 6 plus 10 times 3, 30. So that's 36 oxygens on the left. On the right side, we have 6 plus 5, 6 is 30. So we have 36 oxygens on the right. And then the sulfur, we have a total of 10 times 2, 20. Here we have 5 times 4, 20. So all the atoms are balanced. So let's look at the charges. We have a total of plus 12 here for the 12H plus, minus 2 for 2 nitrates, and then minus 20 for the 10 thiosulfide, or still thiosulfate, I think it's called. Anyway, so that's what, 12 minus 2, that's 10. 10 minus 20, that gives you what, minus 30?
Negative 10. 12
You're
minus
right.
2 is 10.
Yeah, you're right. My bad. Okay, so that's on the left. And then on the right side, what do we have? 5 minus 2. 5 times minus 2. So that's minus 10. So the charges are balanced. So therefore, the equation is balanced. All right? Okay, any questions about this one? Any questions? Yes, ma'am.
Why did you times the second equation by 5?
Because you want to ensure, as he correctly said, you want to ensure that the number of electrons gained is equal to the number of electrons lost. So the equation we had here had only 2 electrons here compared to the 10 here.
Mhm.
But we want to make sure that this number here is equal to that number. And the best way to do that is to multiply this equation by 5. But be careful, because not only do you multiply this by 5, but the entire equation by 5. Right? And that's how we end up with this right here. And then we move to the next step.
Okay, so it's just to make those electrons kind of
Right.
cancel
And
out.
that is true, as I said before, that is true for all redox reactions. The number of electrons lost must be equal to the number of electrons gained, always. All right? Okay, any other questions about this? Any other questions?
So when you're actually doing a redox reaction
Mhm.
and you're actually seeing how it works, I mean, where are the electrons going exactly? How are they changing in order to switch the bonding of everything?
Well, it depends on, and there's a term that we use in chemistry called mechanism. Because usually this doesn't go in one step. Usually it's several steps. So it all depends on the reaction. That's the best answer I can come up with because, and I'm quite sure if you have done any biology courses, you're going to see when it comes to how cells, deal with the transformations of, let's say, glucose to whatever, right? It's always a step-by-step process.
I can kind of see in this, I think the NO3 breaks apart and then bonds with the hydrogen.
Right, yeah. You have to do some detailed experiments in order to figure out exactly what the mechanism is going to be. For those of you who have to do Chem 2, the second chapter that you're going to look at is kinetics. Because very often, and to the end of that chapter, you're going to see the discussion about mechanisms. And usually, in a lot of cases, it's the kinetics that you would use to determine what the mechanism of the reaction is. And every day, you have chemists who are doing just that, doing research on mechanisms of reactions. Okay. Okay, so if there are no more questions about this, I'm going to do one more example. In fact, correction. You're going to do this example. I'm just going to write down what you tell me, right? So let me clear this. And let me, I'm going to make up one again. Hmm. Hmm.
Is that manganese O4?
This is called a permanganate ion. This is manganese.
Okay.
Yeah. Okay. What shall I react this with? Okay. And let me just say, these are just purely hypothetical because I can't tell you that this would actually happen, but I'm just creating these examples for practice sake, all right? Okay. You tell me what to write down. What's the next step?
Write it in the two
Okay.
equations.
So what would be the two half equations?
Chlorine to this 2 to ClO3 minus, and then MnO4 minus to Mn2 plus.
Okay. And by the way, you guys out there in Zoom, you can chip in as well, please. If you have anything to say. Okay, what next?
Balance atoms that aren't oxygen, all right?
Okay.
So Cl2
Mhm.
to coefficient 2 ClO3.
Okay, so put a 2 here. Okay, very good.
And then 2, or not 2, I think the second one's already balanced, right?
Exactly.
Yeah.
Mhm. Okay, so the manganese is already balanced, so we don't need to do anything there. Okay, next step.
We want to add oxygen to hydrogens in order to,
Okay, let's deal with oxygen first.
so for the first one, we'll do 6H2O on the left side.
Okay, very good. What about the second half equation?
Then on the second half, we'll do 4H2O on the right hand side.
Okay. Very good. Next step.
You need to balance the hydrogens on the
Okay.
first equation, so you need to add 12H to the right side.
12H plus. I remember it's H plus, not just H, right? What about the second half equation? Okay, very good. All right, so here is where people tend to screw up. Let's see if you can answer this part without screwing it up. Balancing the charges. Let's deal with the first half equation. How would you balance the charges in the case of the first half equation?
This is where we're adding electrons, right?
Exactly, we're adding electrons. So which side do you add electrons and how many electrons would you add?
Determine the charges of each side first.
Okay, so you have to determine the total charge on each side. Okay, so what would be the total charge on the left side?
There's 6H2O, which is balanced, and then Cl2, so -2.
I'm sorry, repeat that?
Would it be
The left
it doesn't
side.
have a charge now, so is it neutral?
Yeah, it's 0. And somebody just chimed in with a comment. Let me see what this person says. Okay, so Miss Pilgrim is saying 1 electron to the left. Are you talking about this half equation we're talking about? Because I don't think so, but let me not say anything yet. Because we need to determine the total charge on both sides, right? So what about the right side?
The right side should be a +6.
Positive, positive 10, because you have 12 plus charges minus 2, right? So that would be plus 10, right? So to which side would you add electrons, and how many electrons would you add to that side? 10 electrons on the right. That is indeed correct. Okay, very good. What about the second half equation? What's the total charge that we have here on the left?
Uh, 7
Plus 7. And what's the total charge that we have here on the right?
plus 2.
Plus 2. Okay, very good. So to which side would you add electrons, and how many electrons would you add to that side?
Would you add 5 to the left side?
To the what?
To the left side?
Yeah, very good. Add 5 electrons to the left side, because by adding 5, you're reducing that side total charge by 5. That gives you +2, which balances with the +2 on the right side. Okay, very good. So far, so good. So the next step is, let me just erase this down here. The next step is what?
Balance the electrons by multiplying by coefficients.
I'm sorry, repeat that?
Multiply by coefficients to balance the electrons.
Okay, so what does that mean for what we have here? What would you multiply what by? I mean, like,
Multiply the second half equation by 2.
okay, so you multiply by 2, so that means you have to multiply everything by 2. 10 electrons plus 16 hydrogen ions plus, sorry about that, plus, I multiply by 2, 2 MnO4 minus, and then on the right side, you're going to have 2 Mn2 plus 8 H2O. All right? So what I'm going to do is just draw a line through this to avoid confusion, because what you need to do now is add this to this, right? So is there anything that would cancel out on both sides? When you add this equation to this equation, is there anything that will cancel out?
After you multiply by the times 2, yes, the 10 electrons on either side.
Okay, so the 10 electrons will cancel out. But there are some other items that will cancel out as well. Can you identify them?
Will some of the
H2.
positive hydrogens cancel out?
Okay. Yes, so you have 12 hydrogen ions here, and we have 16 here, right? And as she just said, these 12 hydrogen ions will cancel out some of these. In fact, we'll cancel out 12 of these, leaving behind 4. All right? Anything else you think will cancel out?
H2O.
Exactly. These 6 water molecules will cancel out 6 of these, leaving behind 2. All right? And then you add what's left, because there's nothing else that will cancel out. So what's going to be left will be the chlorine plus 4H plus 2MnO4 minus. And then on the right side, you're going to have 2ClO3 minus plus 2Mn2 plus 2H2O. And that should be the final answer, of course. But again, we check to make sure that everything is balanced. So let's do that now. So on the left side, we have 2 chlorines here, right? And we have 2 chlorines here. So the chlorines are balanced. Then we have 4 hydrogens here. And over on this side, we have 2 times 2, 4 hydrogens. So the hydrogens are balanced. Then we look at the manganese. We have 2 manganese here, 2 manganese. So that's balanced. And then we have a total of 2 times 4, 8 oxygens on the left. On the right side, we have 2 times 3, 6, plus 2, 8 oxygens. So the oxygens are balanced. And then we have to look at the charges, right? What's the total charge on this side here? 4 plus minus 2. So that's plus 4 minus 2, which gives plus 2. And then on the right side, what do we have here? Minus 2 plus 4. That gives you minus 2. So the charges are balanced on both sides. Okay, somebody's saying something online. Okay, so Miss Anwar is asking, how do you determine what order to put the final answer in with the compounds or element? Okay, if I understand what you're asking, it doesn't matter what the order of the different substances are, as long as you put them on the appropriate side of the equation, right? So it doesn't matter if you put H plus here or Cl2 here. That's correct, right? But if you put like Mn2 plus here and MnO4 here on opposite sides, that would be incorrect, all right? It doesn't matter the order or the sequencing of the different substances as reactants or products, as long as they are on their own appropriate sides of the equation. So I hope that answers your question, Miss Anwar. Okay, any questions or any other questions about this example? Any other questions? Any other questions? Okay, so that's pretty much it for this chapter, actually. So So what I'm going to do now is let me see, did I publish assignment 4? Okay, no, I didn't. So let me publish assignment 4 now. So you should be able to complete assignment 4 based on what we have done. And what I'm going to do is set up a Dropbox for your submission of assignment 4. Okay, so I'm going to put the deadline as Monday. Oh, so that's today. And this will be Monday. Okay, so make sure you submit your assignment in the Dropbox provided. Make sure it's in a PDF format. And remember all the things I said. Make sure that you write in blue or black ink because that will come out more clearly when I start grading it. Make sure you write your name at the top of each page as well so that I can, just in case things get shuffled up a bit, I can put things together in terms of the assignments for particular persons. Okay, so what I'm going to do now is move on now to chapter 5. I think I've downloaded the PowerPoint here, which deals with gases. And again, much of what we're going to cover in this chapter would be something that you should have been exposed to in your previous chemistry experience, all right? So let's talk about gases. And as we all know, gases are basically one of the 3 phases of matter. You have solid, liquid, and gases. But gases are a bit unique compared to solids and liquids, right? If you look at what happens at the microscopic level, the way the gas particles behave, they're always in constant motion. In fact, their motion can be described as translational, which means that they travel in straight lines until they hit each other or they hit the walls of the container. And because of this particular behavior of gas particles, in terms of the gas itself, they flow readily and will occupy the entire volume of their container. And from time to time, you hear the term vapor. Vapor is a term that is used in association with substances which normally exist as liquids under normal room temperature and pressure conditions. And if you heat it, then it produces the gas. In that context, the gas is called a vapor, right? So as stated there, you can hear the term vapor in relation to water or something like methanol, because those 2 substances are normally liquids, but they can vaporize, and therefore the gas that is produced is called a vapor. On the other hand, if you have gases that exist as gases under normal conditions, like oxygen and nitrogen and so on, then we simply just use the term gases for those particular substances. And what you'll find is that there are many compounds whose molar masses are very low. They can easily vaporize from liquid to gas, or they exist already in the gaseous state, all right? And this is just a list of a few gases and their uses, all right? So you can look at that at your own leisure. So let's talk about the theory that is used to explain all the gas laws that we're going to encounter later on in this chapter. And this theory is called the kinetic molecular theory, all right? The kinetic molecular theory. And there are several assumptions concerning this theory. One of them we mentioned before, that the molecules are very energetic, always moving, right, at high speeds. And they will, as I said before, their motion is described as translational. And we can explain the behavior of gases based on this understanding of what happens at the microscopic level. So, for example, we all know that gases exert pressure on the walls of the container that they're located in. And that can be explained based on the fact that because the gas molecules are always moving at high speeds, then they will randomly hit the walls of the container. So you have literally billions of particles, gas particles, hitting the walls of the container, and collectively that would manifest as a pressure exerted on the inner walls of the container. Another thing we can explain is, for example, the relationship between pressure and temperature, because as we all know, as the temperature increases, the pressure increases. Why is that so? Well, based on the kinetic molecular theory, when you're increasing the temperature of the gas particles gain energy, they become more energetic, they move at a faster pace, or more speeds or greater speeds, and they will hit the walls of the container much more harder, and therefore the pressure exerted by the gas particles collectively would increase as well. So basically, these are the things that we can explain based on our understanding of the kinetic molecular theory, which basically describes the behavior of gas particles, all right, at the microscopic level. Okay, so one of the things I mentioned earlier is the fact that any gas exerts pressure on the walls of the container that they're in. So we need to define what we mean by this term pressure, because in everyday language, people tend to use pressure and force as if they mean the same thing. But that is not true, right? Even though I don't have it here, let me just tell you, and if you have done physics before, you'd have learned this. Force is basically a push or a pull, right? So if I'm pushing on something, or if I'm pulling on something, an object like a chair or whatever, then I'm exerting force on that object, right? Pressure is the force per unit area. So basically, when it comes to pressure, we're talking about the force transmitted over an area, right? And as a result, there's a mathematical equation we can write down to express pressure, I hate writing, in terms of force and area. And that equation is pressure P is equal to force divided by area, right? And as a result of that equation, the unit of pressure is based on or is dependent on the units that you would use for force and area in this equation, right? Now, according to the SI unit system, right, the force is expressed in newtons and area is expressed in meters squared, right? So if you look at this equation where you're going to have newtons as a unit of force and meter squared as a unit of area, so therefore that means that the unit of pressure would be newtons per meters squared, right? And there's a special name given to that unit, right? You can use newtons per meter squared, but there's one particular unit that is equal to that we can use. It's called the Pascal unit. So 1 Pascal is the same thing as 1 Newton per meter squared, all right? Now, the Pascal unit or the newtons per meter squared unit is not the only unit that we use in science, right? For one, we tend to use kilopascals because the Pascal unit is a very small number, right? So for the sake of convenience, in most cases, we use the kilopascal unit instead of Pascal unit when it comes to expressing pressure. But there's some other units as well, right? There's one unit that is known as the atmosphere unit, all right? I'm going to explain how that unit was derived. And then there are other units like the millimeter mercury unit, which I'm also going to explain that one, which is the same thing as a torr unit, right? So the torr unit and the millimeter mercury unit are both one and the same, all right? So I'm just going to show you on the next slide the relationship between these different units. And that's a small table which gives you the relationship. So what they did was that they put 1 atmosphere here on the left and equated to all of these right here, right? So it turns out that 1 atmosphere, by definition, is equal to 760 millimeters mercury. I'm going to explain how we arrive at that relationship shortly if we have the time, right? And as I said before, the millimeter mercury unit and the torr unit are both the same. So basically, that's why these two numbers are the same. Now, to be perfectly honest, I don't anticipate us using this, or this in any future problem-solving exercise, all right? So that's as far as that's concerned. However, this, and this, in terms of the units, I'm quite sure you'll encounter in future problem-solving exercises, all right? So this is just a collection of the different relationships between the atmosphere units and these other units right here, all right? Okay, now, how do we measure pressure? Well, there are two instruments that we're going to talk about in this chapter. One is called the barometer, all right? The other one is called the manometer, which we're going to meet. I don't think we're going to meet it today, so that would have to wait until next class, all right? So let's talk about barometers, right? Barometers are used to measure atmospheric pressure. So I'm quite sure we're all aware that everybody who lives on Earth is submerged in a mixture of gases, right? That's the atmosphere, right? The main constituent would be nitrogen, which is just under 80%, and then oxygen, which is, I think, slightly above 20%, and then you have some other gases, right? So basically, that mixture of gases exerts pressure on everything that is submerged in it, all right? So the barometer is used to measure atmospheric pressure. And let me just say, and I'm quite sure you probably know this, that the atmospheric pressure changes with weather conditions and so on, all right? Okay, so the instrument is used, that is used to measure atmospheric pressure as the barometer, right? So this is where we get a definition of 1 atmosphere, right? In relation to the millimeter mercury unit that we're going to see how this works, right? 1 atmosphere is the pressure exerted by a column of mercury that is exactly 760 millimeters high, all right? We're going to see how that works, right? And this is just a rehash of some of the relationships that we just talked about. The relationship between the atmosphere unit and the millimeter mercury unit and the torr unit and the kilopascal unit. Yes, sir?
Mercury specifically.
We're coming to that. In fact, we may not be able to answer that question today, but next class you're going to see one example I'm going to show you, which shows you the reason why mercury is used. Because that's a good question. Mercury is very expensive, right? And one might be asking, okay, why don't we use water, for example, right? Which is several times cheaper. I'm going to answer that question next class, all right? Okay, so, all right. So let's talk about the instrument itself, right? So I want you to look at this diagram here, right? To the left, we have a trough with mercury in it, and inserted in the mercury is a tube where this end is open, right? So what's going to happen is that the atmospheric pressure will act on the surface of the mercury outside of the tube, but also because this is open, the atmospheric pressure will act on the surface of the mercury inside the tube, right? So therefore, as a result, the mercury level inside the tube will be at the same level as the mercury level outside the tube, right? There's no difference in terms of the surface of the mercury inside and outside the tube, right? Because the air pressure inside the tube here would be the same as the air pressure acting on the surface outside the tube, all right? Now, in this setup here, this is different because the end of this tube here is sealed, right? So the way this would be set up is that you have the trough already filled with mercury, and then you fill the tube with mercury, right? You put your thumb over it, assuming that you're wearing gloves, of course, and then you invert it into the trough with the mercury, and then you let it sit. And what's going to happen, if the tube is long enough, what's going to happen is that the mercury level will fall to about 760 millimeters, right? So basically what this is suggesting is that whatever the atmospheric pressure that is acting on the surface of the mercury on the outside of the tube, that will be the same pressure exerted by this column of mercury at the same level inside the tube, right? And what you'll find is that there's a proportional relationship between the height of the mercury level inside the tube and the atmospheric pressure that is acting on the surface of the mercury outside the tube. And that's where we get this relationship, because it turns out that when they measured the mercury level, the height of the mercury inside the tube, it's about 760 millimeters, right? So therefore, that is where the new unit of pressure comes in. 760 millimeters of mercury is equal to 1 atmosphere by definition because of this setup. Yes, sir.
Mercury, isn't it also in thermometers? That's the red stuff.
No, the red stuff, any thermometer that had the red stuff, that's alcohol. Mercury has a more silver color. I don't think we have any mercury thermometers in our lab. And a lot of schools have discontinued using it because of when it breaks, you have to take special precautions to clean up and all that. So, we use alcohol thermometers.
So they do exist.
Oh, yeah. Oh, yeah. But I don't remember seeing any in this lab or even the lab at Citrus. So, yeah, we don't use, I don't think most schools use mercury anymore, or mercury thermometers anymore. Okay, so that's where the relationship between the atmosphere unit and the millimeter mercury unit was derived from this kind of experimental setup. All right. Okay. Let me see here. Okay. So this question is asking, a Canadian weather report gives the atmospheric pressure as 100.2 kilopascals. What is the pressure expressed in unit torr? So basically, this is a simple conversion type problem. So you're going to start off with, you're going to start off with 100.2. Oh, by the way, again, this is one of those things that's unique about United States. Most other countries, if you were to visit them and turn on the TV and look at their weather reports, they express their pressures in kilopascals. United States, instead, we use millimeters mercury. Yeah, millimeters mercury. That's what they use in the weather reports. Okay, so here we're trying to find out what would be the equivalent value of pressure in torr. So if you look back at the tables that I showed you, you'll see that 101.325 kilopascals is equal to 760 torr, right? So the way we set this up is that we put 101.325 kilopascals below and 760 torr above. And then we do the number crunching. Divided by 101.325. And according to, oh, did I do that right? Let me do this again. 100.2 divided by 101.325 times 760. Okay, so according to my calculations, and please correct me if I'm wrong, but I got 751.6. And the units here would be torr. So that's a relatively simple problem, all right? Okay, any questions about this one? Any questions?
We round it to 4 because of the 102.
Yeah,
kPa?
uh-huh.
Okay. Because the 760 torr is an exact.
Exactly,
Gotcha.
yeah, exactly. Any other questions? Any other questions? Check something here. Okay, let me see here. All right. Let me see here. Let me see. Should I start this? I don't like starting a particular topic and stopping in the middle of it. All right, tell you what, I'm going to call it a day today here because once I start something, I like to finish that particular topic and deal with it that way. All right, so that's it for today, folks. So remember to submit your assignment by Monday, assignment number 4. And I think that's all I have to say by way of, oh, let me get those who came in late. Let me see here. Okay, let's see here. Is Jernigan here? Nelson? Osorio? Randley is here. Talon is here. And Wilbert. Okay, all right. So that's it, folks.
You gonna get our tests back?
I'm going to run them off today. I'm going to scan them and send them to you today. Yeah.
Okay, so you're gonna like submit it in Canvas, like what?
No,
Like,
they email it to you.
Even.
Right. Just like I did the assignments. Right. I'm just going to email it to you.
You're on Citrus tomorrow, right?
Tomorrow I'll be at the Citrus campus from 2 to, make sure I'm telling you the right thing. Citrus 2 to 5.
Will you be here Friday?
Friday from 2 to 5. After class, well, after class and lunch. Yeah.
I feel like I just don't know what went wrong on my test. I did.
Oh, well, like I just said to her, I'm going to send you the,
Yeah.
right, and then if you have questions, I'm also going to post the answer key as well. So you can compare your answers to the answer key, and then if you have questions after that.
What is the next test and what chapters is it gonna be on?
Okay, I know that chapters 3, 4, and 5 will be on it.
Okay,
No, I'm sorry, what did I say? Your first test was what, chapters 1 and 2?
yeah,
Okay, so 3, 4, and 5, definitely.
okay,
I'm not sure about chapter 6 yet, but 3, 4, and 5 for sure.
for sure. And do you know when we're doing it yet?
October, if I'm not mistaken, it's the 17th.
The 17th?
Yeah.
Okay.
That's on the schedule in the syllabus.
How many chapters are there total? 11?
12, I think it is. Yeah.
There's no final.
Here's the final, yeah, which will be comprehensive.
Gotcha. And then you'll drop the lowest test grade, right?
I dropped the lowest of the 3 test scores.
Okay. Thank you.
All right. And you guys